So, based on the last video, you know you have a sample size you can afford in error, time, and cost. That's great. So, if you do not know how to determine the sample size, look in the description for a link to the previous video titled Determining Sample Size. You should also know that your data is normal, it has a mono frequency, and you've accounted for any trends. Again, there's a video linked in the description if you're not sure what that means or if you do have data like that. So how do you know the difference in means between two sample sets is significant? That's what we're going to show you here, but in order to understand that, you have to understand a few more concepts. So we're going to go through those now. First, you need to know the purpose of Six Sigma. In Six Sigma, you learn what the KPIVs, or the key process input variables, are, their impact on the KPOVs, or key process output variables, and how to control the KPIVs. Things like how long a grinding or plating operation lasts, or what percentage of the solution is used. Anything that would be defined in your documentation for how to complete a process and what tools or materials to use in the process would be considered a key process input variable. So by carefully controlling your KPIVs or your KPOVs, I'm sorry, by carefully controlling your KPIVs, your KPOVs, or key process output variables, are under control. Things like how well you fit within your specification for whatever your requirements are for the final product. Six Sigma helps you understand what parameters of your KPIVs control your KPOVs. To gain a better understanding, you may choose to change a KPIV and then see what kind of an effect it has on your output variables. But when you do this, you need to be sure that the difference in the data for the mean or range are statistically significant at 95% confidence level, because there's natural noise and there's natural variation due to random causes in every process. So you don't want to make a change and think, oh, look, our average went up, and you implement something that maybe costs more money, but it's just natural noise. So you want to avoid that, and this is what a t-test helps you with. So next, you must know that there are 4 attributes to a data set. And we're only going to be working with one of these attributes for now, but later videos will discuss the others. So the mean, which is the average of your data. That's one, your main attribute that we'll be working with today. And then there's the range, which is a variation in your process. It's also it's 3 standard deviations above and 3 standard deviations below your mean. That's your range, and that basically tells you how good your process works. So every process has what you call natural noise, which is what you would expect to see with any set of data or any process. So it's what you would expect for a variation. Then there's attributable cause, and that's noise indicating that something has changed. This could be one data point or a shift in data points moving the mean up or down. We're going to talk about these 4 attributes so you understand what they are and the role they play in understanding your data. But for now, I want you to just think about this. You have a mean, a range, you have the natural noise, and then you have attributable cause, which is what we're looking for, attributable cause. So the mean, like I said, is your average, and it can be impacted by many things, which could move it to the left or to the right of the x-axis, or move it up and down. And usually the whole histogram will shift left to right if you change one of your KPIVs. And then there's the range. It's, like I said, 3 standard deviations above the mean and 3 below. This is your natural variation you would expect in your process. The smaller the range, the better your process is under control. Now, if you look at what we've got on the screen here, you'll see that there's +1, +2 standard deviations. There's a upper control limit. There's -1, -2, and there's a lower control limit. And each of those buckets has a different probability of the data being in there. There's a previous video that talks about that in more detail. We're just going to stick with how to do a t-test. But ideally, you want your range of your process to be 75% of your specification range or less. So if your specification is 100 to 200 units, whatever they are, your specification range is 100 units. So you want your natural process variation range to be 75 units or less. And for a good CPK, the mean of your natural process variation range needs to be in the middle of your specification at about 150 units. This is called process capability or CPK. If not centered, this impacts your CPK, but not your PPK, because your PPK is really just more of a percentage of how well, a percentage of your process variation versus your specification. It doesn't really matter if it's centered or not. CPK tells you if it's centered as well. Don't worry about these terms for now. Just want you to understand that the mean and range are and kind of how they relate to performing a t-test. So next, you must also know that there are two types of noise or variation in every process. There's natural noise, which is the natural variation in your process, and it can be ignored for the most part. Notice how all the points on the graph here are within all the lines. Then there's what we call attributable cause, which means something's happened to your KPIV to push your data outside their normal noise limits. This occurs when a KPIV changes or it's not under control. If you see the red dot in the upper right, that would be an example, just one example of attributable cause. There's more examples described in a video linked in the description, but you kind of get the idea. Something's going on here, and we always use 95% confidence level. I'll explain more of that in detail later. So this is another example of attributable cause. In this case, something's changed to move the data up. If you look at the orange data dots and the blue dots, maybe they're collected from two different machines. Maybe the orange machine is getting worn out or whatever, but they are two separate groups. And then you would test this to ensure that the difference is statistically significant at 95% confidence level with a t-test. If you did it, it would tell you that the difference in the means of the two groups is statistically significant. And Excel can do this. I'll show you how to do that in a minute. So you don't need expensive software to do these things. So first, you have to add the analysis Toolpack to Excel if you haven't done this already. So you open Excel. I'm going to open up Excel. Basically, you go to File, Options, Add-ins, and then you add an analysis Toolpack. I'm going to show you how to do that real quick here. Go File. Oops. Over here. Oops, I think I got the wrong thing here. File. Here we go. That's interesting. File. Here we go. Options. Add-ins. Yeah, that threw me off there for a second, hiding that options on me. I already have it added, but you'll find it down here. Just click it and say okay, it'll add it to it. I cancel this. Okay, so once you've added it in, then what happens is you can pull this file up. If you look up where data and you see a data analysis, that'll show up over here. So I see I got my data analysis, but before we get into the data analysis portion of it, I'm going to show you a few things here that you have to understand. I put a set of numbers in the yellow highlighted areas in columns B and C. These are random numbers between 2 and 25, and then they're added together. You can see rand between 2 and 25 plus rand between 2 and 25. What this does is it randomly selects a number between those two and then adds them together, and that actually will make a histogram. Okay, not a perfect histogram, but definitely something that's going to pass the normality test. So it's going to produce numbers between 4 and 50. want you to notice how the means are not the same. And this is often the case with random numbers and natural noise, and even with sampling. I'm going to show you a few things here. Look at the means, 26. They look pretty close together here so far, 26.7, 26.8, and your standard deviations look pretty close. But I'm going to cycle through here, and I want you to see how they can change. So they're not always the same. And you can see they're pretty close though. And the reason why is we've got about 1,000 samples here. Now, if I was to cut that back to, let's reduce this 1,034. 1,034, and we're going to change it to just 34. So we're only going to get like 30 samples. Okay, so now I want you to watch, because of now I got a smaller sample size that I'm taking this from. Um, you're going to see now that mean, and the difference between the means and the standard deviation is even more. And this kind of plays along with what we'd learned in the last video about sample size. Higher the sample size, the better off you are. We're going to leave this at just 31 for now and move on. So what we want to know is how the difference in these means. Is it statistically significant, or is it just natural noise? And a lot of times you're not going to know that just by looking at it, because you're going to need a t-test to tell you that. So the t-test will tell you if the difference in the mean or the average of the two sets of data is statistically significant at 95% confidence level. What I'm going to do here is I'm going to lock these in place so that they don't confuse us later. I'll just do this paste special, and I'm going to do values. It's basically taking that formula out. So I just got numbers in here. And what I'll do is I'll go to this data analysis. I want to scroll down. And what I want to do is I want to use this t-test to sample assuming unequal variance. It's just the one that's probably the most robust. I'm not going to explain why, but you don't really need to know a whole lot about why. We've got the variable range, and typically what I'll do is I'll take the first one with the highest standard deviation. So I'll take this one here. It's got the highest standard deviation, and I'm going to do the same here. And then my hypothesized mean difference, I'm just going to put 0. I'm going to say my hypothesis is at 0. And because I included, come on. Okay, come on. Yeah. All right, it's back at the top now. Because I included this top description, I'm going to tell it I've included some labels. My alpha is going to be 0.05, and that just basically means 95% confidence level. We always use that. I'll explain that in more detail in a minute. My output range here, I want to use this because I've got a formula down here that's going to tell me the result. So once I have all of this on here, I can hit OK, and then it's going to tell me that's overriding some data. And if you're using a spreadsheet, you'll get this. Just say OK, and if you're not using it, you probably won't get it. So what it says down here is the difference in the means between population 1 and population 2 is not statistically significant at 95% confidence level. Now, in order for it to be statistically significant, your t-stat must be greater than your t-critical. Okay. Now, you see this negative sign here? That's because I took population 2 and first instead of population 1. Now, what you can do is you're going to get the same result if you reverse them. The only difference is you'll have a negative sign. So what I have down here is I look for the absolute value. So I say, what's the absolute value of this? If the absolute value of T stat is greater than the absolute value of T critical, then the difference is statistically significant. But as you can see here, the absolute value is not larger. So it's not statistically significant at 95% confidence level. Now, if we were to go and do something a little bit different here, I'm going to try something else here. Rand between 5 and 50 plus rand between 5 and 50. And then we're going to zip this down. Oops. Oop, come on. You're going to make it hard for me, aren't you? Come on. I put that formula inside here. So now I got a totally different population. Now we're going to do, that's pretty different. We're going to do the same thing. Leave everything the same. I'm going to overwrite the data. And there we go. The difference in the means of population and population 2 is statistically significant at 95% confidence level. Now I want you to think about something else for now. I need to think of this. And you're probably wondering, why are we using 95% confidence level? Well, that's the typical thing that we use in statistics. Let's say that you and I agree to flip a coin to decide who buys lunch for the whole week. Today's Monday. I flip the coin and it's heads and you buy lunch. Because every time it's heads, you buy lunch, tails, I buy lunch. Well, I have a 50% chance, okay? Basically, it's going to occur 1 and 2 times. I'm going to get heads. If I flip a coin twice in a row, 50% chance, all right? Let's go to Tuesday. Tuesday, it's heads. Now, every coin flip is independent of the previous coin flip. However, whenever you're flipping coins in a row, the odds of getting 2 heads is about 25%. Because think about it, on Monday, we could either have heads or we could have tails because we had 1 coin. That's 50%. Okay. Tuesday, we have a 25% chance because we could either have a head on Monday and a head on Tuesday. That's what we're looking for. Or, or we could have a head and a tails, or a tails and a head, or a tails and a tails. So only 1/4 of those combinations, or 25%, are there 2 heads in a row. So this occurs about 1 in 4 times. Wednesday, I'm not going to do all the math here for you, but basically Wednesday we flip the coin, it's heads against. You got about a 12.5% chance that this occurs 1 time if you flip a coin 3 times in a row, 8 times. There's an 87% chance it's not going to occur naturally. Thursday, what would you think about Thursday? If I flipped the coin and I said I got heads again, there's only a 6.13% chance. That's basically this might occur 1 time if you flip a coin 4 times in a row, 16 times. You got a 94% chance it would not occur naturally. And Friday, heads. So finally, you're probably thinking either yesterday or today, you're thinking something's up. So you take the coin and you flip it, and it's heads again. And that's only a 3% chance. This is 1 in 32 times. If you take a coin and you flip it 5 times, and you do that 32 times, 1 time in 32, you might get 5 heads in a row. There's a 97% chance this would not occur naturally. And you look at the coin and you find it's a 2-headed coin. And then I'm buying lunch for the next month. So what are the odds that a person would win 6 coin flips in a row? Well, that would be about 1.6% chance, or 1 in 64 tries. When flipping a coin 6 times in a row, you might get it 1 time. But that's what a presidential nominee claims to have done in 2016. I think there was attributable cause here, because that's not natural noise. Remember, uh, there are lies, damn lies, in statistics. Numbers never lie, only people do, and often they manipulate the numbers to support their lies. So unless you know what somebody did and how they collected data and filtered their numbers correctly, never believe any statistics you hear. That's just the way I live. The funny thing is, once you understand these statistical concepts, you can very easily debunk statistical claims that are made on false or doctored data. It's really easy to show or prove that somebody's doctored the data. So, like I said, somewhere around Thursday or Friday, people would naturally say, something's going on here. And rightfully so, because something was going on. So, in summary, add the analysis Toolpack to Excel. Use the sample size you determine to be the best based on the previous video in this series. Change your process. Use the t-test to sample assuming unequal variance for your current data sample and your proposed process data sample. Variable 1 must have the higher standard deviation, or ask the Excel file, ask for the Excel file that I used, or just look at your absolute values. Next, we're going to talk about an F-test. This tests for a difference in the variation or your standard deviation or basically your range of your data. And this is usually the hardest thing to impact. Tightening up your standard deviation is harder than just moving your mean. But this deals with identifying sources of variation and natural noise, which need to be better controlled to make your process range smaller. It's not easy, not impossible. So if you found this video useful, like it, subscribe to the channel, and share it with anyone else who may find it useful. If you didn't find a video useful, then subscribe in the hope that an upcoming video will be. Eventually, we're going to go through projects using Lean Sigma and Six Sigma tools, as well as the tools needed to support them. Remember, a wise person learns from their mistakes, while a genius learns from the mistakes of others. So until the next video, keep data clean and take care.